Welcome to the 36th Theoretical Physics Colloquium by Professor Duncan Brown, who is a Charles Brightman Professor of Physics at Syracuse University. He got his PhD at the University of Wisconsin-Milwaukee in 2004. He was a postdoctoral scholar at LIGO Lab and Theoretical Astrophysics and Relativity Group at California Institute of Technology. After that, he received a faculty position at Syracuse University, and since 2015, he is the Charles Brightman Professor of Physics there. He received numerous awards and honors over his career. In 2008, he received National Science Foundation Career Award. In 2009, he became Kavli Frontiers Fellow, 2014 Fellow of the American Physical Society. He received Cottrell Scholar Award and Scilog Fellow Award in 2010 and 2015 from Research Corporation for Science Advancement. In 2016, he shared Gruber Cosmology Prize with the LIGO Scientific Collaboration. And 2016, he also shared a Breakthrough Prize in Fundamental Physics with the LIGO Collaboration. He received numerous teaching awards. At Syracuse University, he does a lot of service for the community and professional community. He is a member of the Board of Trustees of Internet 2 since 2017. As a member of LIGO Collaboration, he served on multiple committees for collaboration, and I guess with that, I'll stop. His research interests and experience of gravitational wave astronomy and astrophysics, search for gravitational waves from compact binary coalescence with the LIGO and Virgo observatories. He is an expert in numerical relativity and its applications to gravitational wave detection, third-generation gravitational wave detectors, high-performance computers, and much more. Today, he will be talking about neutron star binaries, discovery of gravitational waves, and many other things, I assume. So with that, I'll give the microphone to Duncan.
Okay, so thanks, Igor, for inviting me. It's a pleasure to talk to you today about what we've learned about binary neutron stars since the discovery of GW170817, the first neutron star binary to be observed in gravitational waves. So let me first start with a little bit of background for people who might not be familiar with gravitational waves. So this is the kind of classical sketch of what a gravitational wave is. So you know from undergrad E&M that when you have a charged particle and you move that charged particle around, accelerated charged particles generate electromagnetic waves. Well, it's a consequence of Einstein's theory of general relativity that as massive objects move around, they generate gravitational waves as the curvature of space changes. And the curvature of space propagates out at the speed of light, and the strength of the gravitational wave signal is given by the strain, and that's the change in length divided by the length. So the physical effect of a gravitational wave is to stretch and squeeze space-time. So two freely falling objects will experience what's called geodesic deviation as the distance between them changes, as these ripples of space-time pass through, as the space-time metric changes, and the strength of that gravitational wave is given by the strain, the change in length divided by the length. And unlike electromagnetic waves, where you need a dipole moment, so there's no monopole radiation in E&M because you can't have charges just appear and disappear because of conservation of charge. You can have dipole radiation. In gravity, there's conservation of mass and angular momentum, so the lowest order radiation you can get is quadrupolar radiation. So you need two objects, and what's pictured here is a kind of a cartoon of two black holes orbiting around each other, and as you get that quadrupolar change, the change in the quadrupole nature of the gravitational field, it propagates outwards, carrying away energy and angular momentum from the system. So the challenge here of detecting these, so it's basically been a 100-year quest to find gravitational waves. They were first predicted by Einstein fairly quickly after he wrote down his general theory of relativity. And then there was a 50-year debate in the community about whether or not these waves actually existed physically or whether they were a coordinate effect of GR, and were just a mathematical artifact. They were mathematical waves, but they weren't really physical waves. And it was only in the 1950s that Felix Pirani came up with an argument that if you had two masses and you attach what you call a dashpot between them, so you attract something that generates, that has friction between these two masses, as the gravitational waves go past, he demonstrated that the change in the curvature of space-time would actually heat up the dashpot through the friction, and so you'd actually deposit energy in there. So the gravitational waves have to carry energy for that energy to appear due to the friction of the. Feynman generalized this to a sticky bead argument. So you probably heard the sticky bead argument of two beads on a stick, and it heats up the bead. Heats up the stick as the beads move backwards and forwards. So these things carry energy. So the first 50 years of the field was debating whether or not these things even existed, and then the second 50 years of the field was building detectors that could actually measure them. And it took 50 years to do this because the strength of these gravitational waves, so the change in length divided by the length, is very small. So the physical constants here, when you calculate what typical strains are by dimensional analysis, the constants here conspire against us. So if you calculate the typical strain from a gravitational wave, it goes as g, Newton's constant, which is a small number, divided by the speed of light to the fourth power, which is a very big number. So immediately you've got a very small number out here. Then you've got the non-spherical part of the kinetic energy of the system. So this is the energy associated with that quadrupolar motion, divided by the distance to the source. And in order to have enough kinetic energy here to overcome this very small number, you can't generate this in a lab. You can't do laboratory experiments to generate and detect gravitational waves because the waves radiated are so small. The classic example is, if you shake your fist, there's a time-changing quadrupole moment. What's the strain generated? And it's something like 10 to the minus 45 strain. So you can't do this on the lab scale. So you need extremely dense, extremely massive objects moving very fast to get kinetic energy big enough to overcome the small coupling constant here. And that means they're going to be astrophysical objects, they're going to be black holes or neutron stars, which are not going to be very close to us, fortunately. So R here is going to be a big number, the distance to the source. And so when you put all these together and you calculate the typical strain for, say, two 1.4 solar mass neutron stars at a distance of 100 megaparsecs or so, you find the strain is about 10 to the minus 21, which is a very small number, very difficult to measure. And that kind of is the short reason why it took 50 years to build detectors that can measure these. But even though the strain is very weak, don't let anyone tell you that the strain is very small. Don't let anyone tell you that gravitational waves are very weak. The luminosity radiated in gravitational waves is enormous. So if you calculate the luminosity radiated as two objects go around each other, it goes as c to the fifth, and that's a big number, divided by g, so divided by a small number. So I've got a really big number here. It goes as the velocity to the sixth power, and then it goes as the size of the system compared to the system's Schwarzschild radius to the inverse square. And again, if you plug in typical numbers there, you end up with 10 to the 59 ergs per second, which is a huge amount of luminosity. Compare this to the solar luminosity, which is 10 to the 33, or gamma ray bursts, which kind of peak at 10 to the 52. When two binary black holes merge together and generate gravitational waves, they outshine all of the stars in the universe put together. This is a huge amount of energy. So really what you want to think of is not that not that gravitation is weak per se, but it's really, space-time is really stiff. It's really hard to get that energy into space-time, but you put a lot of energy in that radiates out. And it's hard to get that energy back out, which makes it really hard to build the detectors. To give you an idea of kind of the scale of the challenge of measuring strains of 10 to the minus 21, in order to measure a change in length divided by a length of 10 to the minus 21, effectively you need to build a machine that can measure the distance between Earth and Proxima Centauri, the nearest star to the sun. That's a distance about 4.2 light years. You want to be able to measure that distance to a precision of about 10 microns. So that's the change in length divided by length that you're talking about of a strain of 10 to the minus 21. So this is an incredibly precise measurement. And again, that's why it's taken 50 years to build these machines to do it. But we have built these machines. We're actually on the second generation of these machines right now, the Laser Interferometer Gravitational Wave Observatory, or LIGO. And this is a diagram that shows how Advanced LIGO works. So as I said, the physical effect of a gravitational wave is to stretch and squeeze space-time, so change the distance between two freely falling masses. And to measure that strain, we use something that is you've probably encountered in undergraduate lab. It's basically a Michelson interferometer. So at its simplest, you take a laser beam, you shine it through a beam splitter, bounces off a mirror, comes back, bounces off another mirror, comes back, comes to a photodetector. And if you keep the length of the arms exactly the same, you can set this up so you get constructive interference going back towards the laser, so all the light goes back down here, and destructive interference going towards the photodetector. And as these arms are stretched and squeezed by the gravitational wave going past, you get a change in the length of this arm relative to this arm, and light will leak out towards the photodetector. So in principle, tabletop Michelson interferometer could detect gravitational waves if the gravitational waves are strong enough. But to get these strains of 10 to the minus 21, we need this machine, which is Advanced LIGO. And basically what happens is you have a few more optics to make this more complicated. You take a laser beam, you bounce it against the beam splitter. The beam comes off here, and when you calculate the optimal arm length for an interferometer to measure gravitational waves, what you realize is you want the light to be stored in the gravitational wave detector's arm for half a gravitational wave cycle. So you get a cycle of stretching, but it's not canceled out by the subsequent cycle of squeezing. So you want to store it for half a gravitational wave cycle. If you look at the frequencies of gravitational waves that are accessible to Earth-based detectors, they're around the 100 Hertz regime. So two binary neutron stars will sweep from very low frequencies up through the tens to hundreds of Hertz and coalesce at kilohertz frequencies. And so you're looking at the 100 Hertz frequency. You calculate what arm length you need to store half a gravitational wave cycle, and you realize you're dealing with arms that are of order 100 kilometers long, which is not really very practical to build. So what you do is you put two mirrors here, you set up a Fabry-Perot cavity, and you bounce the light backwards and forwards between these mirrors 100 times on a 4 kilometer long length, which is practical to build. And so you effectively give yourself 400 kilometer long arms by reflecting the light backwards and forwards 100 times on average between these mirrors. Then it comes out of these arms, it recombines at the beam splitter. The waste light going back towards the laser, you bounce that back in with this power recycling mirror, and that makes it look like you have a more powerful laser, which is good because you have a more powerful laser, you have more photons in the detector, you have more ability to measure the phase fronts of the light, and so you have a more sensitive gravitational wave detector. Then the gravitational wave imprints itself as audio frequency sidebands on the laser carrier light, comes out here. And what you actually do is you bounce those gravitational wave sidebands with this thing called a signal recycling mirror back into the detector. So you flip the phase of the sidebands, and then you can actually pick up that other half of the gravitational wave cycle coherently, and you can make the gravitational wave detector more sensitive by this signal recycling. So Advanced LIGO, you take your simple tabletop Michelson interferometer from undergraduate lab, and you make it a dual recycled, power and signal recycled, dual recycled Fabry-Perot, because it has these Fabry-Perot cavities in the arms, Michelson at its heart, interferometer. And if you design this, you look at the fundamental noise sources. At the low frequencies, you're limited by seismic noise. This thing is suspended from wires that are on our active seismic isolation platforms. You don't want anything else moving the mirrors. You don't want seismic noise to couple into those mirrors and cause the mirrors to move. So the low frequencies, this plot shows the strain, the amplitude sensitivity, the amplitude power spectral density, of the noise in the detector as a function of different frequencies. So bigger numbers is bad because that means more noise, more power in the noise at a given frequency. Lower numbers are good because that means less noise power at a given frequency. So down here, you're dominated by the low frequency seismic noise. Then you have quantum noise here, which is a combination of radiation pressure on the mirrors from the lasers at low frequencies and photon shock noise at higher frequencies. And then you have a noise source here, which is a fundamental noise of the Brownian motion. This is the atoms on the coatings of the mirrors jiggling around and giving you a random noise source here. You add all these together and you end up with this design noise curve right here, which is the design noise curve at Advanced LIGO. And this thing is sensitive of strains of order 10 to the minus 23. So now we have a machine that can actually detect gravitational wave strains from astrophysical sources of gravitational radiation. This is what it looks like in practice. So if I look at, I have this cartoon here of these two couple pendula hung from this thing. That's what this thing looks like in practice. This is the end test mass of the LIGO Livingston detector. So the laser beam comes in here, bounces off this mirror, comes back, and all this stuff up here is basically isolation to get this mirror here to approximate to be a freely falling test mass, free from all other influences as best we can. in the sensitive band of the detector. So all it sees is the changing space-time metric as the gravitational wave goes through the observatory. This is what the observatory looks like in Hanford. So the beam splitter and laser in here, and the photodetector in here. They come out. Here's the one of the end test masses. Here's the other end test mass, and these are 4-kilometer long arms. LIGO operates 2 observatories. This one is in Washington State, near the Hanford Nuclear Reservation, and this one is in Livingston, Louisiana, it's equidistant from Baton Rouge and maybe a bit further away from New Orleans. So this is in Louisiana, and again, here's the corner building, and then you have the end test mass over here, and the end test mass all the way over here. Inside here is a stainless steel beam tube that has the ultra high vacuum with a concrete cover over it, mainly protect it from people either driving trucks into it or shooting at it, depending on which site you're actually at. Both of those have happened at the 2 different sites. This is the sister detector in Pisa, near Pisa in Italy. This is Virgo. So this is a French-Italian gravitational wave detector with a very similar design to the LIGO detectors. The key difference is this has 3-kilometer long arms rather than 4-kilometer long arms. So it makes it 3/4 of sensitivity because the sensitivity scales as the arm length. But we have 3 detectors. So we have a worldwide network of 3 detectors operating and listening for gravitational waves, these ripples in space-time from astrophysical objects. And these detectors began operating in 2015, very quickly after the LIGO detectors were turned on. In fact, even before the observing run was officially declared to begin, even while we're still in an engineering shakedown, there was a discovery of binary black holes, gravitational waves from binary black holes, the famous GW170817 event, that prompted the opening of the field of gravitational wave astronomy. But I'm not going to speak much about black holes today. What I'm going to focus on today is binary neutron stars. And what you can see here is an observation made by that network in 2017. So this is GW170817. So this is August 17th, 2017. And what you can see here is the data from the 3 detectors, LIGO Hanford, LIGO Livingston, and Virgo. And this is shown in what we call the time frequency plane. So we have time along the x-axis here in seconds. So this is 10 seconds, 20 seconds, 28 seconds is the far left axis here. And then gravitational wave frequency in hertz between 50, 100, and 500 hertz on this picture. And then what you do is you take the data coming out, you construct a sequence of Fourier transforms of the data to get frequency domain slices, and you plot the power in each frequency as a function of time to get these time frequency diagrams. And so the color bar here shows the normalized amplitude, so the amount of gravitational wave amplitude in each different frequency.
Duncan?
And, for about the first 10, yep.
There is a question here in the chat. The question comes from Kirill Boguslavsky. The quantum noise seems to be among the strongest sources of noise. Is there a fundamental bound of how much this noise can be reduced, and what are the challenges there?
Yes, so there's a the quantum limit is a fundamental limit. So you're basically hitting up against the uncertainty principle. That's what really dominates you. You have delta E, delta T greater than or equal to h bar over 2. And so what you're doing is you're measuring the timing of the phase fronts of the light arriving at the beam splitter, and you have an uncertainty relationship that you can't know the energy and time precisely. You can't know the phase and time precisely. It's equivalent to the more familiar delta X, delta P. So you actually have the Heisenberg uncertainty principle that gives you a standard quantum limit there. You can turn the laser light up, and that reduces the shot noise. Really what is happening is vacuum fluctuations are coupling into the interferometer. And so there are techniques to beat the standard quantum limit if you squeeze what you do is you squeeze the vacuum going in. So you squeeze the vacuum correlations going in, and so you put the uncertainty into the amplitude and out of the phase. You can use squeeze light techniques to reduce that and beat the standard quantum limit. But there's a fundamental physical limit there that you can that you're stuck with for a given arm length of a detector. If you make the detector's arms longer, then you increase the strain sensitivity that way.
Thank you.
Okay.
So this is the so what you can mostly see here is the noise in the gravitational wave detector. But what you can see is a time frequency track, and you can see it most clearly in the Livingston detector. This is the most sensitive detector. So you see a time frequency track here of a gravitational wave signal buried in the noise, sweeping up in frequency and amplitude, coming up here from, it becomes visible around kind of 25 hertz, about 30 seconds before merger, and then sweeping up and kind of disappearing into the noise up here as the two stars merge. And so this is and you can see the same signal in the Hanford detector. I'll note you don't see anything in the Virgo detector. I'll explain that in a second. So you see this coincidence signal here beautifully in a time frequency spectrogram. And this was the very convincing detection. The universe loves gravitational wave astronomers. Our first binary black hole event was an incredibly loud binary black hole event that was so loud you can just bam past the time series and make a plot. And that's in figure 1 of the Discovery PRL. Beautiful loud signal. Our first binary neutron star signal is a beautiful loud signal that you can do some very naive signal processing techniques and see the signal in the time frequency domain in both the Livingston and Hanford detectors. So the universe has been very kind to gravitational wave astronomers. Given that you have 3 detectors here, you can actually localize on the sky where the signal came from. So I can point my network, and the fact there's no signal in Virgo is actually very constraining, because gravitational wave detectors are not equally sensitive in all directions. They have a null direction where you get an equal amount of stretching and squeezing in both arms, and you don't get a differential change in the arm length, and the signal vanishes. And that's in a particular direction, kind of down the diagonal of the arms. So the fact that you don't see it in Virgo actually gives you very good constraints, not just the timing, the time of arrival in the 3 detectors, but the amplitude from Virgo gives you very good constraints as to where this signal came from. An alert was sent out, and you know, the vast majority of the time domain astronomy community followed this up. And the image I'm choosing to show is from a collaboration that I was involved in, the DCAM collaboration. And what was discovered was this optical counterpart to the gravitational waves. And so you have this optical counterpart. So this is not just a gravitational wave discovery, it's a multi-messenger discovery. And what's shown here is the fading of the kilonova, the optical counterpart, 14 days post-merger as it fades away. So this is the host galaxy here. And this is the light of the kilonova that was formed in as the 2 neutron stars smash into each other. You've got 2 city-sized atomic nuclei banging into each other at 1/3 the speed of light. And that's the flash of light that you get from that merger.
Duncan, there is another question.
Yep.
Will Gilroy, do you want to ask yourself?
Sure. Hi. I was wondering if it's just my eyes or if the shape of those signals in the Hanford and Livingston detectors look a little bit different to me right at t = 0. I don't know if it's just me, but if they're different, I was wondering if there's a reason for that.
No, they're actually, one of the things that we do to check for that a detection is real is look for signal consistency between the 2 detectors. And you do that not by making these time frequency spectrograms, which are nice to look at, but you do that by match filtering. So you do that by correlating the time series of the detectors against a template signal that is calculated using fully either a post-Newtonian or fully relativistic calculation of the signal. When you do that, you find the signals match very exactly. The problem is you have all these speckles here in the detector data, and your eye gets fooled by the noise speckles as well as the actual signal in here. So when the calculation is done properly, it's not just done for this visualization, it's done with optimal match filtering against a set of template waveforms, and that gives exactly the same signal in both detectors.
Got it. Okay, thank you.
Okay, so now we've got this beautiful multi-messenger detection of gravitational waves. There are many, many things you can do with it. This demonstrates that short hard gamma ray bursts, the progenitor of short hard gamma ray bursts is binary neutron star mergers. You can constrain the speed of gravity compared to the speed of light by looking at the arrival time of the gamma ray burst that accompanied this, was detected by Swift, by Integral and other gamma ray burst detectors. There's a whole, you can look at the Hubble constant. There are many, many things you can do with this discovery. I'm going to focus on one aspect of this, which is to look at the equation of state of the neutron stars. And this is an interesting thing to look at because the equation of state of cold ultra-dense matter remains poorly constrained at high densities. This is a big open topic in physics. So what we're looking at is the cold equation of state. So at T equals 0, the equation of state relates the pressure to the density. So standard equation of state relationship. And we can look at the equation of state of nuclear matter, and there are many nuclear experiments. So there's P-REX, lead radius measurements. There's FRIB coming online at Michigan State. There are many nuclear experiments that have been done and are planned to look at constraining the nuclear equation of state. But these can really only constrain the EOS up to the nuclear saturation density of about 3 × 10⁻⁴ grams per centimeters cubed. But the densities of matter in the cores of neutron stars are about 10 times the nuclear saturation density. And so if we can look at neutron star mergers, we can explore the equation of state at much higher densities in regimes that are not accessible to terrestrial experiments. So that's what I'm going to talk about for the rest of the talk. So this is a plot that shows how the equation of state imprints itself on neutron stars. So this is a plot that shows for a given equation of state, so all these things here, alpha1, alpha2, BSK, blah, blah, H4, these are all different nuclear equation of states. So I can come up with some particular nuclear theory, and I can predict a pressure versus density graph from that, either from QCD, first principles, or I can do it from various different approximation techniques. And so all of these different families of equation of state curves come from different approaches to solving the nuclear equation of state problem. And when you calculate how they impact the behavior of a neutron star, so this is for a single neutron star, I have a relationship between the neutron star's mass and the neutron star's radius. So each one of these curves corresponds to a choice of equation of state. And the equation of state gives me the mass-radius relation. So it says if a neutron star has 1 solar mass, for this yellow equation of state here, AP3, then it's going to be about 12 kilometers in radius. If the nuclear equation of state was MS1b, which is this purple curve, then that neutron star would be over 14 kilometers in radius. So this is how the equation of state couples into the neutron star. And we typically call these equation of state curves down here, these are the soft curves, so these are compressible. So for a given mass, these will give me a low radius neutron star because I have fairly compressible nuclear matter. And out here, I have my family of stiff equations of state. So I push down, gravity pulls down on the nuclear matter, it can push back more stiffly, and this is going to give me a large radius neutron star for a given mass. So how does this imprint on the gravitational waves? Well, what I'm showing you here is a full numerical simulation of 2 neutron stars merging from each other from the simulation of Roland Haas in 2016. So what you can see is the gravitational waveform as a function of time. And as the 2 stars orbit around each other, you get this gravitational waveform until they finally coalesce and merge. And what's being shown here is the fluid bodies of the neutron stars. And you can see that these aren't perfectly spherical. You get some tides raised on the neutron stars. And it's this tidal deformation of the neutron stars and then its imprint on the gravitational wave signature that lets you explore the nuclear equation of state from the inspiraling binaries, from the 2 binaries, 2 objects going around each other. As I get later into the signature, so now I'm looking at the merger here, you get these tidal tails of matter thrown off. So you get this neutron-rich matter thrown off. And this is what powers that kilonova explosion. So this gives me a weak gravitational wave signal, but an electromagnetic signature from the radioactive decay of the material in here, which may be powered by some hypermassive neutron star in the center right here. And then afterwards, I'll just mention it briefly, for different equation of states, you can get different post-merger signatures, but these aren't detectable for GW170817, so I'm just going to mention these briefly to say that they exist. Perhaps future gravitational wave detectors will be able to get at this post-merger signature of the ringing of the neutron star. But I'm going to focus on the first 2. So how do we get the information about the gravitational waves out? Well, as I said, the information that gravitational waves is encoded in the phase evolution of the gravitational waves in that in-spiral regime. And what you find is you can write down an expression for the gravitational wave phase as a function of time. And this was first written down by Peters and Matthews. They wrote down what's called the 0pn term. So 0pn is 0 post-Newtonian. This is basically just saying, let me take Newtonian physics and I'll just add in the leading order loss in energy in gravitational waves from the Einstein quadrupole formula. And so instead of energy being conserved in an orbit, like it is in Newtonian physics, I'll let the energy leak away in gravitational waves according to the Einstein quadrupole formula. And then you get the leading order term in the gravitational wave phase evolution, which you find depends on something called the Chirp mass, which is this combination of the two masses of the two stars. So M1, M2 to the 3/5 over the total mass to the 1/5. Then as you do higher and higher order GR corrections, you end up with a first order post-Newtonian correction, a third order post-Newtonian correction, and these add in more and more GR corrections to the waveform. And you find that when you get to fifth order, actually you should say this parameter here, eta, is the mass ratio. So the mass ratio of the binaries enters in at first order post-Newtonian. And then at fifth order, you get a term that depends on the equation of state. And so the equation of state corrections are actually relatively high order corrections to the phasing, but they have a big coefficient in front of them. So you can actually hope to measure them by tracking the gravitational wave phase. So how do these tidal effects enter the post-Newtonian gravitational wave phase? Well, we typically parameterize these by this term lambda, the polarizability, the tidal deformability of the neutron stars. And that's the ratio of the induced quadrupole moment to the applied tidal field. So I have two neutron stars in a binary. This star generates a gravitational field, a tidal field that this star feels, and it gets a tide induced on it, and vice versa. And so this term here describes the tidal polarizability of each star in the other star's tidal field generated by the other star's gravity. And if you do some dimensional analysis on this, you find that you can write a dimensionless polarizability that goes as lambda over m to the fifth, which we often write down as this for comparability to other fields of physics that look at this tidal deformability. This is the Love number here, K2, and then this quantity here is the compactness to the minus fifth power. So m over r to the minus fifth power. So this is basically just a dimensionless version of this tidal polarizability. Why are we interested in this quantity? Well, this quantity depends on the mass of the neutron stars, the radius of neutron stars, and the equation of state through K2. And it imprints itself on the gravitational wave signal as this term lambda tilde. You remember, it'd be really nice. So it'd be nice if we measure M1 and M2 directly from the gravitational wave phasing, but we don't. We measure Chirp mass, the combination of M1 and M2. We measure that at leading order, and then we can try and separate that out into M1 and M2 with the higher order effects. Here, again, you don't measure lambda 1, the deformability of one star, and lambda 2, the deformability of the other star. What you measure is the joint tidal deformability, lambda tilde, which depends on the polarizability of the first star, the polarizability of the second star, and this quantity Q, which is the mass ratio of the two binaries. So M2 divided by M1, the mass ratio of the binaries. So when you measure the tidal effects, you're actually extracting this lambda tilde quantity. Really what you want to get at is K2 and R, so you need to have some way of backing this out from the gravitational wave signature that you measure. So it's challenging to measure this, but one good thing was demonstrated by a paper by Thibaut Damour and collaborators back in 2012. I won't go into this in too much detail. So they looked at, this moment here says, it asks the question, at what gravitational wave frequency do I get the information about different pieces of the physics of the binary signal? And in cyan here, you have the Chirp mass. That mostly comes from low frequencies. This thicker line here shows the mass ratio, which they denote as nu, the mass ratio. And then this line shows where most of the signal to noise ratio is accumulated. So you get most of the information on the mass and mass ratio at low frequencies. This lambda t is where you get the information on the tidal deformation from, and it comes out at high frequencies up here. So it's challenging to measure. It's a hard post-Newtonian effect. It comes from late in the in-spiral signal where the detectors are less sensitive, but it's a secular effect that accumulates over many cycles, so you can track it. And the good news is, because it appears at different frequencies, it's not degenerate with other parameters in the gravitational waveform. So you can actually access this from the gravitational waves. So having detected GW170817 and having a model for what the physical effect of tidal deformability is, we can look and we can see if the gravitational wave signal shows evidence for finite size effects. Are these two neutron stars inspiring around each other, or is this a black hole waveform for which lambda equals 0 for both stars? And we can use Bayesian inference to decide this. That's a standard method. I model the waveform with and without tidal deformability. And I can look at the base factor that compares for GW170817. I can calculate GW170817 modeled as a binary black hole system or as a binary neutron star system. And I can do that with different equations of state for the binary neutron stars. And I can do what's called model selection, and this paper describes the methods we use. Model selection to look at the nature of the signal. And we can calculate specific base factors for different equations of state. So this is one of these equation of state plots with a bunch of different equations of state. Calculate the base factors. And what you want is a very large number here. That says that this is basically the odds ratio between, is it a binary black hole signal or is it this type of neutron star signal? And you find that for the stiff equations of state, you do get fairly large odds ratios. So these are ruled out at 1 to 10 to the minus 5, 1 in 100. But as you get to kind of the mid-range equation of states, and then towards the softer equation of states, you find base factors of order unity. And if you have a base factor of order unity, what that means is you can't really distinguish between one model and the other model. And so we can, with GW170817, we can rule out the stiffest equations of state at high confidence. But soft equations of state and black holes, in fact, are all consistent with GW170817. So the gravitational waves alone can't tell you for sure that this system is a binary neutron star system or a binary black hole system. It can rule out very stiff neutron stars, but it can't rule out the latter two. But black holes are black, and we know that the system is not dark. This is the Hubble image of the kilonova. So this is a nicer picture taken with Hubble of the host galaxy here, and here's the kilonova. So we know that the system involved at least one and most likely two neutron stars. So we can proceed under the assumption that this actually is a binary neutron star system, and we can go back and we can reanalyze the gravitational wave signature and see what we can learn about the tidal deformability, and hence the equation of state of the stars. And there's been a bunch of these analyses done. There's analyses that are agnostic to the neutron star equation of state, and then analyses that assume these are binary neutron stars and place constraints. And I'll talk about two of these analyses that my group's been involved in recently. So a first analysis led by Shomi They in collaboration with Jim Latimer and Ido Berger, and then a recent analysis led by Colin Capano that does a more multi-messenger analysis. So the first analysis we did, we said this takes advantage of the fact that if you look at these equation of state curves and you look around 1.4 solar masses, which is where GW170817 is thought to have its masses, and these curves are all pretty vertical. It doesn't matter which one they are, but they're all fairly vertical around that mass. They tip over here, they tip over here, but at the masses we're interested in for 170817, they're all pretty vertical. And that means that for almost every specific EOS in the mass range relevant to 170817, the change in radius is actually very small. And you can use this to put what we call the common EOS constraint. So you basically assume that both the neutron stars have the same equation of state physically. That makes sense. There's only one nuclear equation of state in the universe. But you can use this, the fact that the change in radius is pretty small, to approximate R1 to be R2. And the tidal deformability then goes as the mass ratio to the 6th power between the two. So this is how one way we can back out a radius measurement from measuring the tidal polarizability if we assume this common radius constraint on the neutron stars. So this is the first analysis that just used the gravitational wave signature alone, and this placed a constraint that the radius of neutron stars is about 10.8 kilometers with a 90% confidence interval of 8.9 to 13.2 kilometers. And so this is work that was done back in 2018 by Shomi and collaborators. So this is the first gravitational wave constraint on the neutron stars that is constrained that these are binary neutron star systems. But we have more than that. We have a bright signature. We have a multi-messenger discovery of gravitational waves. We don't just need to look at the gravitational waves alone. We can look at what happens afterwards. So Shomi's analysis just looked at the in-spiral phase here. But as that in-spiral moves into a merger, that the fate of the binary is determined by the masses and the equation of state of the compact objects involved. When these neutron stars merge, one fate could be prompt collapse to a black hole. If the merger remnant has enough mass in a small enough radius, it will immediately collapse and form to a black hole. Another thing that can happen is you could form a hypermassive neutron star. This is supported by differential rotation, that eventually when it spins down, it collapses to a black hole. Or if the maximum mass of the neutron star is high enough, you could actually end up with a rigid rotating neutron star that is supported by, over its spin down time, by just the rigid rotation of the neutron star. That could collapse down. This is a supermassive neutron star. That could collapse down to a black hole, or it could spin down to a neutron star. And the fate of the neutron star depends on what goes in and on the equation of state of nuclear matter as to whether you promptly collapse, you have a hypermassive neutron star, supermassive, or a neutron star remnant. So we can use the kilonova light curve. So this is more observations of this is an observation of the kilonova light curves, the optical afterglow of the merger over 18 days. And these kilonova light curves, the shape and evolution of these kilonova light curves suggests that we have what's called a blue-red kilonova signature. So a red kilonova signature is a kilonova that's just powered by the radioactive decay of those tidal tails of neutron-rich matter that are thrown off. A blue kilonova is also powered by emission from the hypermassive neutron star that gives you blue kilonova ejecta, internal shocks in there. And so one model of this is the Metzger-Thompson and Quatert model. So the kilonova light curve suggests that we have this red-blue kilonova. So it suggests that we actually have a hypermassive neutron star, and we can't directly collapse to a black hole. So the multi-messenger signature not just constrains to the inspiral objects and neutron stars, but also that they can't directly collapse to a black hole. The merger remnant also places a constraint on the maximum neutron star mass. The remnant neutron star can't be too long-lived, or there'd be too much energy EM observation. So we kind of have a Goldilocks situation here, right? It can't die too soon, it can't live too long, and the window it can live in to give you just the right kilonova signature depends on the nuclear equation of state through the maximum mass of the neutron star. So what we did to bring all of these together, so this is a paper led by Colin Capano in collaboration with Ingo Tooze and Sanjay Reddy's group at University of Washington. We constructed a set of physically plausible equations of state using chiral effective field theory. And these were calibrated against nuclear experiments. So we used things like the P-REX results to use terrestrial nuclear experiments to calibrate the chiral effective field theory up to nuclear saturation density. And then we use these chiral EOSs to directly marginalize using over equations of state using the gravitational wave observations. We apply one end of the kind of this Goldilocks constraint that the merger remnant didn't immediately collapse to form a black hole. And then we apply the other constraint that the neutron star can't be too long-lived and it has to collapse eventually to form a black hole, so we don't have too bright a kilonova signature predicted that disagrees with the observations. So if you put all these together, this kind of shows the sausage making process. Each one of these curves, now we have many families of equation of state curves on this mass radius diagram. And we compare each of these to the gravitational wave data using Bayesian analysis, and we get posterior probabilities for the equation of state, for the radius of the neutron stars, and for the masses of the neutron stars. So this is our prior on the radius of the neutron stars. One set of equations of state calibrated up to nuclear saturation density, another set of chiral effective field theory equations of state calibrated up to twice nuclear saturation density. So depending, you can pick either the brown or the blue, depending on how much you trust the calibration of these chiral effective field theory equations of state. Then you apply the gravitational wave constraint, and that reduces these priors on the radius into these posteriors, where you have the median value and the 90% confidence interval and credible interval here. Then you apply the prompt collapse threshold that produces an additional constraint. Then you apply a constraint on the maximum mass of the neutron star, and this is where you end up with what is so far the best constraints on the neutron star radius from the multi-messenger observations of 170817. And this is Shomi's result for comparison with some other results here. And so this multi-messenger constraint is the best constraint we have on the neutron star radius so far. What can you do with that? Well, one interesting thing you can do is you can say, well, what does that imply for future detection? So we can use constraints on the neutron star radius to determine the tidal disruption in a neutron star black hole binary. So now we have a better constraint on the EOS and the tidal deformability. We can say, what happens if I have a neutron star going around the binary black hole? This is a signal that's not yet been seen. It's a very interesting signal for many reasons. And one thing I can ask is, okay, I think, binary neutron star signals, I've seen 170817, I think I should get these kilonova signatures, there are good predictions for these. But what do I see if a neutron star is swallowed up by a black hole? Will I see an electromagnetic counterpart? To get that, I need disruption of the neutron star before merger. If the neutron star is swallowed whole, then I'm not going to get disruption of the neutron star, and I'm not going to get an EM counterpart. The neutron star just disappears whole down the event horizon before being disrupted. I get no signature. So what we can do is we can use our results from 170817 to predict, given the spin of the black hole and the mass of the black hole, and for a given neutron star masses, so a 1 solar mass neutron star, a 1.4 solar mass neutron star, or a 2.3 solar mass neutron star, we can ask where we'll actually get tidal disruption. This depends on the spin of the black hole and the mass ratio between the two objects. So the more highly spinning the black hole, the more likely I'm to get disruption, and the higher the mass ratio, the more likely I'm to get disruption. So above these lines, I get disruption. And the challenge is it's going to be very hard to get EM counterparts for 1.4 solar mass neutron stars falling into black holes, unless the black hole is rapidly spinning. So I'd say it's unlikely that NSBH merger is going to produce EM counterparts, or if they do, there'll be more of the red counterparts, faint red counterparts. Again, projecting forwards, this is just a little side comment. Given this diversity of signatures, whether it could be a red kilonova, or a blue kilonova, a neutron star black hole, one challenge for observing for observers is to prioritize their observations. Given that it's going to be really hard to see these neutron star black hole afterglows, you're going to have to invest a lot of telescope time in them. Whereas a binary neutron star might have a much brighter counterpart and be easier to see, like it was in 170817. So it's very important that we get out very quickly the parameters of the any signals detected in low latency by the LIGO-Virgo network. And so one of my graduate students, Daniel Finstead, recently led a project to look at how quickly you can get out. So this would be of interest to any observers on the call. How quickly can you get out full posterior parameter estimates of the component masses of the neutron stars, M1, M2, and if you have a neutron star black hole binary, also get an estimate of the spin of the black hole. So the mass of the neutron star, the mass of the black hole, and the spin of the black hole, which is critical for figuring out how much time you want to invest in following up these signatures. And it turns out with this method of Zaki et al., this rapid parameter estimation measurement, Daniel generalized that to a full detector network, simulated an advanced LIGO-like population. And for plausible populations, you can actually get the parameter estimation out in less than 20 minutes. So this is sufficiently fast to be able to tell the observing community you can get the masses and spins, and you can go ahead and point. The accuracy is not great. So this shows the accuracy of the component masses and the spins. You have fairly wide estimates on the mass and spins. So you're not going to say, this is a 1.37 solar mass neutron star compared to a 1.41 solar mass neutron star, but you can get broadly accurate enough to say into what class of systems does this fall into, because you're getting the masses to about 10% or so. Let me just talk briefly about GW170817. So the existence of 190425 is nice because it proves that it's a second neutron star binary detected by LIGO and Virgo in the third observing run. It's a single detector event. One of the detectors was down at the time, so that we weren't able to do follow-up of this event. There's no sky localization, but it's a strong enough event to actually detect in confidence as a single detector event. Its distance is about 160 megaparsecs compared to 40 megaparsecs for 170817. But the really interesting thing is its total mass is about 3.4 solar masses compared to 2.8 solar masses for 170817. So 170817 was kind of the canonical 1.4 solar mass in spiral that everyone had talked about for years. But 190425, as well as being a second event that's consistent with a neutron star merger, it's a higher mass event. So it proves that a diversity of neutron stars exists out there in the universe, which is exciting for sampling not just the equation of states, but that mass radius curve, that we'll be able to see the equation of state at different points along the mass radius curve. Unfortunately, the signal's weaker than 170817, so you actually get even less information about tidal deformability out of here than you do from other systems. But what about looking forward? So this figure shows predictions for the binary neutron star rate in per cubic gigaparsec per year that was predicted a long time ago when we were looking at in 2010, trying to predict what the rates for Advanced LIGO might be. Where does that stand now in the benefit of hindsight of now having looked at the first observing run of LIGO Virgo, the second observing run, and the collaboration just published the O3A analysis, this GW170817, and using that and the detection of one BNS in O2, another BNS in O3A, they were able to place a constraint on the rate. And so this gray box here going from about 80 to 800 per cubic gigaparsec per year is currently what the rate predictions are. So this is, kind of in line with what people were predicting a while ago. Some of the more optimistic predictions have been ruled out, but it's things are looking good for detecting more of these as the observatories come back online. Let me just switch gear. I've talked about linear tides so far. I just want to point to a couple of other things you can do with the neutron star discovery of 170817. So as well as the experience of the tidal deformability of each star, so the one star's gravity tidally deforms the other as a fluid body, the energy from the tides can actually couple into interior oscillations, into pressure and gravity modes inside the neutron stars. And Nevin Weinberg proposed in 2013 that this can actually excite a non-linear, non-resonant instability of P and G modes that would be an additional energy sink for the orbital energy of the neutron stars, heat up the neutron stars and cause them to inspiral more quickly. And Reed Essick and collaborators developed a parametric model for modeling these PG mode instabilities in the gravitational wave data. And the LIGO Virgo collaboration published a paper that looked at 170817 and said it's consistent with a signal that neglects these PG mode tides. So one of my graduate students, Stephen Reyes, took a closer look at this recently with calculating these base factors. And what he basically showed is that the consistency of the signal is in fact due to a degeneracy between the standard model waveforms, the standard post-Newtonian waveforms. The chirp mass there is actually degenerate with the physical effect that these PG mode couplings produce. And so you can hide these PG mode couplings in chirp mass or vice versa. They can mimic each other. And so any measurable effect of these nonlinear tides are ruled out. So there's been an argument in the theory community about whether or not these nonlinear tides really do exist, whether they do, whether they don't. The problem is that with gravitational waves, the observers can't really answer that debate because of this degeneracy. Remember I said one of the key things from the result of Thibault's paper was that linear tides are not degenerate with the other parameters, but these nonlinear tides are degenerate. So unfortunately, it's hard to measure these things without much more precise measurements that are not going to be accessible for a while. What about other physical effects in the binaries? One thing you can look at is constraints on the eccentricity of the binary. So there have been a number of models proposed for the formation of binary neutron stars. Have they formed in the field from the evolution of two main sequence stars that have been orbiting each other for all of their lives? Or are they formed in, say, globular clusters by direct capture mechanisms, where you might form an eccentric binary as two stars come close to each other in a dense stellar environment, or maybe triples that involve supermassive black holes and the cause of galaxies, and end up with some residual eccentric signal that might be detectable by LIGO. And Amber Lennon, who's a graduate student in my group, used the 170817 and 190425 signals to look into this. And she looked at the change in the gravitational wave signature predicted by this paper of Moore and Eunice, or a whole number of papers that predict the effect of eccentricity on gravitational waves, going back to the first Peters and Matthews papers at the beginning of kind of the waveform predictions. And Amber did this analysis, again, using a Bayesian analysis to put constraints on the eccentricity. There's a mild degeneracy in this case between eccentricity and chirp mass, as you can see from this plot. But the constraints on the eccentricity for 170817 and 190425 are both pretty low, both in the kind of 10 to the -2 regime at the 90% confidence. And field binaries are predicted to have an eccentricity of 10 to the -4. So these signals are perfectly consistent with field binaries and are not consistent with some of these more extreme direct capture scenarios that people have been predicting. In the last few minutes, let me talk about what we could do going forward. So I've talked a lot about Advanced LIGO results and Advanced Virgo results. I want to just look forwards now to what the field might look like for, any graduate students are online. I was told when I started, so I started my PhD in 99, and my PhD advisor, Bruce Allen, said, you could be the graduate student who discovers gravitational waves. And he just neglected to mention that I would be a tenured faculty member by the time it happened. So if you are interested in looking forwards into the future and getting involved in something that's really exciting, Cosmic Explorer is the next generation of ground-based gravitational wave detectors. So one way that you can get past these fundamental limits in the shock noise, in the quantum noise, in the other noise sources, is just make the arms of the detector longer. The strain sensitivity of gravitational wave detector scales as the arm length. So if you take LIGO, and instead of having 4 kilometer long arms, you have 40 kilometer long arms, your gravitational wave detector is now an order of magnitude more sensitive. And the beautiful thing is, because gravitational waves go as 1 over r, the amplitude of the gravitation, you measure amplitude, not power in a gravitational wave detector, it goes as 1 over r, you can go in the generation of detectors from, initial LIGO didn't see anything. Advanced LIGO seeing black holes and neutrons, black holes and binary neutron stars, and we'll likely see a lot more stuff in the coming decade. 15, 20 years from now, Cosmic Explorer could be seeing every single binary black hole signal in the universe. So you'll be able to basically see out all the way through cosmic time to see these binary black hole mergers with Cosmic Explorer. So I'm showing the O2 horizon. This A+ is a possible upgrade to Advanced LIGO. You're seeing these black holes here. A+ will get you out here. Cosmic Explorer will get you every binary black hole merger in the universe, and probably most of the neutron stars as well, given for reasonable predictions of the star formation rate. Very briefly, it's a 40-kilometer L-shaped detector on the Earth's surface, 14-centimeter wide laser beams, 2-megawatt laser. There's a lot of R&D progress needed in optical coatings and quantum noise and thermal compensation. And it's expected to be online around 2030 at a cost of about $1 billion US. The National Science Foundation has been strongly behind this. They've funded, I'm involved in currently what's called the Cosmic Explorer Horizon Study. This is basically to take the big picture science goals for a third generation detector and turn them into a concrete design for Cosmic Explorer that then we'll have a broad community discussion of. And if the National Academies decide to move forwards, we'll start with preliminary design and conceptual design studies leading towards construction. It's a two-stage approach, just like LIGO is. Cosmic Explorer 1, if you hear about Cosmic Explorer 1, it's just take LIGO and make it bigger. Cosmic Explorer 2 is then an upgrade to that, where you swap out the glass mirrors in Cosmic Explorer 1 and put in silicon mirrors. They have better properties for the coatings and better squeezing to beat the standard quantum limit, and you get an increase in sensitivity to Cosmic Explorer 2. So this is the phased approach to Cosmic Explorer. If you're interested in Cosmic Explorer, we have an open consortium. We're welcoming participation from the broad astronomy astrophysics community. There's no bar to joining. It's a consortium. We welcome people to join. And if people want to visit that link, they can sign up for the consortium and get updates and participate in developing the science case. And we're very open collaboration, and we welcome anyone who's interested in third generation detectors to sign up. So let me just briefly talk about some of the physics you could do with Cosmic Explorer. And again, returning to nuclear physics, one thing that you could do with Cosmic Explorer is you could look at gravitational wave signatures from core collapse supernova. So Advanced LIGO could detect the core collapse supernova in the galaxy, but it doesn't have great fidelity, and it's really hard to pull out the parameters. These core collapse supernova signatures, as you get the iron core basically builds up the Chandrasekhar mass, it collapses under gravity, the material basically free falls, producing a massive burst of neutrinos as the nuclear matter undergoes inverse beta decay, all these neutrinos stream out, it collapses down until it basically hits the nuclear equation of state. It overshoots, bounces, and comes back out. It's rotating as it's doing this. And then you get this ringing of the proto-neutron star as it you basically smack this proto-neutron star with the bounce phase. And so you see the core collapse and bounce right here, and then proto-neutron star ringing afterwards. This is the gravitational wave signature of a core collapse supernova. And the core collapse and bounce signature depends strongly on the rotation speed of the progenitor star. That's interesting to people who study massive stars. And then this post-merger ringing depends on the nuclear equation of state again, because it depends on how stiff that neutron star is when it's ringing down. And so what we can do is we can look and see if we can optimize Cosmic Explorer to look for supernova. So this is a project that Varun Shrestha, one of the students in the Syracuse group, led to look if we could optimize Cosmic Explorer to detect core collapse supernova. And it's good news and bad news. The good news is, you can see out to 70 kiloparsecs and 95 kiloparsecs, which is similar to Dune, the planned neutrino detector sensitivities. But the bad news is there's a lot of empty space between us and Andromeda. So you're getting really good fidelity to core collapse supernova that happen in the Milky Way or in the Magellanic Clouds, but you're not getting out far enough to see stuff that's happening in Andromeda. So the rate is pretty low. You're still at the kind of 1 per 50 to 1 in 100 year rate. But if we did see something, if we did see a core collapse supernova, it would be really exciting because it's another multi-messenger detection. We'd likely get light. So we've got another 1987A, we get light, we get neutrinos, we get the gravitational waves. This would absolutely be beautiful. And we should be due for one by another 1987A by the time Cosmic Explorer is online. The universe loves gravitational wave astronomers, right? They gave us a binary black hole, a binary neutron star, so Cosmic Explorer is due a supernova. So what we can do is we can extract information about the equation of state, and also primarily from the rotation of the proto-neutron star by looking at these supernovae. It's much harder to do this with supernova waveforms because for binaries, we have this very good post-Newtonian model of the signature. For supernova, it's much more challenging because we have to numerically model the signature for different rotations of progenitor star, for different equations of state. You have to generate using principal component analysis, a different basis set that you project the detector against. You can't just compare it directly to the waveforms. All these complexities that I'll refer you to Chaitanya's paper to look at, but we can develop this method for extracting it, and Chaitanya did this. And what we find is, so this table here shows the coupling between the equation of state and kind of this F peak, the proto-neutron star ringing frequency. And we find that for a galactic progenitor with actually a fairly slowly rotating progenitor star, and I give this as the worst case scenario, things actually improve the more quickly the star is rotating, the better things get. The 90% credit interval on measuring beta, which is the ratio of the kinetic to the rotational energy, is 0.2 for Advanced LIGO and improves by an order of magnitude for Cosmic Explorer. And for a galactic supernova observed by Cosmic Explorer, we could constrain the peak frequency to within about 10 hertz, which starts to give us a different, not as good as the in-spiral. I would say, who's going to do better, in-spirals in Cosmic Explorer or supernova? It's going to be in-spirals because they're more precise, but it's a very different look at the equation of state from different physics. And with Cosmic Explorer, we can start to get a handle on the different equation of states from looking at the proto-neutron star ring up. So there's a lot of rich physics in there that we can get out. So I'll conclude there by saying that 1717 has opened up a new area of equation of state constraints. We can now use gravitational waves to explore the nuclear equation of state. Upcoming detections, which hopefully we'll see more of as LIGO comes back online, will provide more information from both gravitational waves and EM. And the future's bright as Advanced LIGO upgrades and Cosmic Explorer comes online to give us precision measurement of neutron stars, post-merger signatures, and possibly even supernova. So I'll stop there and thank the National Science Foundation, as well as my collaborators who have participated in all this research.
Well, thank you very much. Thank you very much for a very nice presentation. Now we will have some time for questions. Any questions from the audience? I see one. Efrain Ferrer, go ahead.
Yes, well, first, thank you for your interesting talk. Larissa, I want to see if you can comment about the possibility to have a equation of states that are related to quark matter, because I saw that most of the M versus R curve that you were showing was for nuclear matter.
Right. So let me go back to this plot. So you can't see it very easily in this plot because the lines are all on top of each other. Actually, I don't know if I can see it. So if I go to this plot here, so when we did this study using the so two parts. Two parts to this question. So one is looking at phase transitions from quark matter in the in-spiral phase. So if you look at these equations of state, the chiral effective field theory equations of state that we looked at actually did allow phase transitions in here. And that's where you get these if you look at these curves right here, these are equation of states that actually allow phase transitions. Now, you don't really get them around where 170817 is, because it's at 1.4 solar masses. So you don't really probe these very well. But when we did the work with Colin and Ingo, we actually allowed these. So you know, if you got more massive neutron stars and you could access these, you could maybe start to get a handle on these from the in-spiral. And I know Andrew Steiner and Katerina Ciacianu have papers on looking at the phase transition effects from the in-spiral signature. Another place you can get it, which is particularly exciting for Cosmic Explorer, and I think is more likely, is in the post-merger signature. So as you get these as the two neutron stars merge, current gravitational wave detectors don't have much sensitivity to that post-merger signature, but Cosmic Explorer will have very good sensitivity to that post-merger, to the gravitational waves from post-merger, and that will let you probe first-order phase transitions in the neutron star. If you get, because you have a situation where you're dumping a lot more mass in a post-merger object than you will get from a core collapse supernova, right? So core collapse supernova, as soon as you hit the Chandrasekhar mass, it starts to collapse, and you might get some matter falling in, but it's generally around 1.4 solar masses. In a merger, you're creating a post-merger remnant that has much more than 1.4 solar masses, and that I think is very exciting for exploring first-order phase transition in quark matter. Because you can look for that in the post-merger signature, but there's no sign of it in 170817. People have looked for it, but there's no evidence for it.
Okay, and no strange star, no? Because I saw that at the beginning you put also the core for strange stars.
Yeah, there's no again. I think that we're going to need to look at the post-merger. There's no evidence for weirdness of kaons or strangeness in the in-spiral 170817, but you can't see the gravitational waves from the post-merger, so you can't probe that well enough, and it will need more sensitive detectors to do that.
Okay, thank you very much.
Okay, next question, David Boschke.
Yeah, thank you for a very interesting, enlightening talk. I have found a recent publication by Eleonora Troya and her collaborators, University of Maryland, who observed 1,000 days, sorry, after the merger, now X-rays, and they find some kind of indications that there is something still powering the afterglow of the merger in the X-rays, and they even discuss the possibility that there might be a pulsar. So what is your personal opinion on that? The leftover of GW170817 might be.
I actually deleted that slide from my. Let me see if I can switch to. I had a slide on that I skipped, so let me add an extra slide in at the end. Can everyone see that?
Yeah.
So this is the results from so Troy's paper is the one I know is the MNRAS.
Yes.
So yeah, so this is really exciting, right? Because this is what it's being shown is that the what you have is the evolution of the kilonova is really cool. It's like, this is the perfect signal, right? You're immediately seeing a gamma ray burst, right? So immediately you see a GRB powered by the merger. Then you see tidal tails, nuclear decay of the matter, also powered by the hypermassive neutron star briefly, and you get this red-blue kilonova. Then you get expansion of the media. You get the widening of the jet angle, so it gives you information about the GRB, and then you also have the emission as the ejector plows into the interstellar medium and gives you radio emission. And so people have tracked this over basically since 170817 happened. So people have been tracking this for almost 2 years now, and they have very good constraints on the viewing angle of the binary. And this is important for the model of the progenitor stars. So there's a lot of argument about exactly what type of EM counterpart this was. Was it, do you have a cocoon of nuclear-rich material that the GRB jet is punching through? There's all these, choke jet, top hat models, all this type of stuff. And so I think it's now pretty conclusive based on the Troy observations, and then the Caltech group, Kunar Muli's observations were published in Nature that's the radio. I think it's pretty consistent that what we're looking at is a successful jet cocoon model where you have material thrown off, the GRB jet punches through that cocoon, it plows into the interstellar medium, and we're looking at it with a jet opening angle of about 5 degrees, and we're looking between 15 and 30 degrees off axis to where we are. So that's kind of what all these observations put together are telling us. And one of the first multi-messenger things we did, again, I skipped this, Daniel Finstad, one of my grad students, combined the measurement of the distance to the host galaxy with the gravitational wave signature to get a gravitational wave constraint on that opening angle. And the beautiful thing is that was done a few months after discovery, and the late time observations of the radio and the X-ray they're giving that open example are all consistent with those early gravitational wave opening angle estimates. So we have a really nice model of what happened for this. It's the textbook. It is the textbook signature.
So yeah, but my question was, so is it so can we so how likely is it that the leftover is a pulsar, not a black hole?
It is very unlikely that the leftover is anything other than a black hole, because if the leftover was a pulsar, it would be dumping too much energy into the electromagnetic signature, and it would have given us a very different EM signature. So the way the light curves evolve strongly suggests that you've got a short-lived hypermassive neutron star that then collapsed down to a black hole. So
but nevertheless, Troya and collaborators discuss this as a possibility in that paper.
I don't think that's likely, because it would have changed the early time signature. I think what is more likely is what they're seeing is off-axis emission or other emission from the nuclear decay or from interaction with the ISM.
They show some indications that the X-ray somehow gets a little bit more luminous than it should be, according to the models they are using.
It's hard to fit that explanation at late times with the observations at early times.
Late times. So that paper is about what happened after 1,000 days.
Right, but if you have the pulsar remnant assumption after 1,000 days, that's really is in tension with what happened early on, that we have good observations for with that you didn't get too long-lived a remnant, because the neutrino wind from the early neutron star would have given you much brighter emission in the blue and for longer than we saw in the neutrons in the early emission.
Okay, thank you very much.
Okay.
Okay, we have some question in the chat here, so I'll read it for you. How will we separate the multiple signals arriving when you are at maximum sensitivity in 2030? So assuming that you will be starting to seeing everything all at once, how can you separate them?
That's an interesting question, and that's a topic of ongoing research. So the nice thing is that the techniques we use are things are fairly linear, right? The match filter is a linear operator, so things add together fairly nicely. The signals are additive on top of each other in the detector. It makes it challenging, but it's not impossible. So right now, the LISA, so the space-based detector, so LISA is running a series of what they call mock data challenges. So LISA will have actually a confusion problem. So LISA has so many white dwarf binaries in the producing gravitational waves in the galaxy that they actually are a confusion noise for the detector. And then they have very loud supermassive black hole signals they have to subtract to get down to the weaker and weaker and weaker signals. So people have already started working on this problem of overlapping signals for the LISA detector. We're working on it. It's one of the things that my group is working on for Cosmic Explorer. it's challenging, but there are methods to deal with it. I mean, one thing you can do is you can take a stretch of data, and in your Bayesian model, you can put an extra parameter in there, which is n for the number of signals in there. And if your signal model is n signals, each of which has a set of parameters, it becomes more computationally intensive, but it's not more conceptually difficult to kind of model what's going on. You let the Bayesian algorithm go over the number of signals and try and lock on the number of signals and get that. But it is something, and one of the things we're actually starting in the Cosmic Explorer Consortium, we hope to bootstrap over the next year, is a set of mock data challenges. People are interested in developing techniques to do this. People are looking at all kinds of techniques from traditional Bayesian analysis with match filtering to machine learning. And so this is, it's a good question. It's not impossible, but it's an active topic of research to demonstrate that it can be done with precision.
Okay, sounds good. Next question from Henry De Jong. Go ahead, ask yourself.
Hello, thank you for a really nice talk. I had a question. I know there are a lot of parameters. You mentioned it before, that it could be a neutron star and black hole merger may give a very weak EM signal, but is it possible that a neutron star could merge with a black hole without any EM signal, or one that is so short in duration for us not to be able to detect any trace at all?
Yes, it is. So it is entirely possible. So if I look at this is a fairly busy plot. So let me explain it in a little bit more detail. So this is the a plot that shows when you'll get the EM signature for and just look at this curve here, for a 1.4 solar mass neutron star falling into a black hole of this mass and this spin. Given a 1.4 solar mass neutron star, above this line, you'll get disruption that can power an EM counterpart, but below this line, you won't. So if a 1.4 solar mass neutron star falls into a 10 solar mass black hole that has a dimensional spin of 0.2, it will just be swallowed whole, and you'll get no EM counterpart whatsoever. So that's an example of the type of system you just asked about. Everything over here is in that regime. In order to get an EM counterpart from a 1.4 solar mass neutron star, I have to fall into either a relatively low mass black hole. So my black hole has to be kind of 2 solar masses, which is challenging to produce. Or I have to have, for the type of black holes we've seen so far, kind of 15 solar masses, it has to be close to 1 is maximally spinning, so the spin has to be very high. So if my black hole lives up here, I'll get tidal, I'll get disruption and might get an EM counterpart. If my black hole lives down here, the neutron star is a swallowed hole and there's nothing.
Okay, thank you. That's still kind of hard to believe it would swallow a neutron star whole like that.
Neutron stars are fairly compact, and so
yeah.
so it can disappear without enough tidal disruption to get the tidal tails.
Thank you.
Okay, next question, Axel Brandenburg.
Thanks, Duncan, for your extremely wonderful talk. I very much appreciated that. I have a question regarding the Cosmic Explorer. So with the length of 30 kilometers, you must also increase the laser noise, right? So does it not at the same time degrade? So how come you are still making a major gain? And this a follow-up question, what do you see as the future of optical clocks by comparison?
So the nice thing is as you scale the arm length, most of the fundamental noise sources just scale directly as the length of the arms. And so the challenge you get is as the things trade off against each other. So as I make the arms bigger, obviously the spot size on the mirror gets larger. That's one thing you do, because you have a Gaussian beam supported between these curved mirrors. If I have a bigger spot size on the mirrors, I sample more of the mirror surface, so I average more over the fluctuations on the mirror surface. So I actually have lower average thermal noise because I'm more averaging over the surface of the mirror. So as well as just the, I'm measuring a strain. So everything just goes in because it's delta L over L, right? Delta L is whatever it is from the binary. L I can control 4 kilometers or 40 kilometers. And so that's really where the length enters. It's just in the delta L over L. Make L bigger, and I get a bigger delta L for a given strain sensitivity. I do hit problems with the standard quantum limit. So as I make the laser more powerful, I get more radiation pressure on the mirrors, so I get more fluctuations there. And that you really need. So one of the challenges in developing this is going to be developing frequency dependent squeezing. So you actually want to, when you squeeze the vacuum that goes in that gives you either the radiation pressure at low frequencies or the shot noise at high frequencies, you actually want to change the quadrature of the squeezing, right? Because where you get radiation pressure, that's amplitude uncertainties. So I want to squeeze an amplitude and put the noise into phase there. And then as I go up to higher frequencies, I don't care about the amplitude as much, I care about the phase uncertainty. So I want to squeeze in phase and put the uncertainty in the amplitude. So you actually get this rotating squeezing as you go across the frequency band. That's one of the big challenges. It's been demonstrated, it's been used in practice to a certain extent in LIGO right now. But that's going to be one of the big challenges over the next decade, to get that frequency dependent squeezing at a level where you can hit these noise curves. But delta L over L always wins, right? You just make L bigger and you get a bigger delta L for a given strain. All right, yeah. Okay, thanks. Yes, and optical clocks instead of using for interferometry in future. I think that, so people have talked about matter interferometers. I don't think they're going to be competitive. So I don't think the optical clocks are going to be competitive with the traditional laser interferometer and then over the CE timescale. The people have, one of the things that I've not been directly involved in, because my primary research isn't experimental, but Stefan Barmer, my experimental colleague, has been involved in, is he's been doing a comparison study between the matter interferometers, between optical clocks, between interferometers, and gravitation. The traditional jewelry cycle Fabry-Perot still has the edge in the frequency band by quite a bit, even compared to the matter interferometers over the next 2 decades. I haven't mentioned the third way of detecting gravitational waves, which is another timing experiment, which is pulsar timing. Yeah, so right. Exciting coming up in the next decade is actually optical clocks using pulsars as clocks. And if we can time the pulses from pulsars well enough, you can look for very low frequency gravitational waves propagating through the universe as they change the time of arrival of pulses coming from pulsars. Yeah, yeah. That's right. Very low frequencies, even lower than right.
Okay. Any other questions? I don't see anything else from the audience. So if there are no more questions, I would like to use the opportunity to thank the speaker. Thank you, Duncan, for a very nice presentation. And thank you, everybody, for coming. I guess with that, we will wrap this up.
Great. Thanks for inviting me.